No, I will not do it. Yes, no, I will. No, okay, very good. It's okay. I can continue or wait. Here, I will give you the slides. You have other exercises to check for characteristic equation. This Lotka-Volterra competition system and predator-prey model. We can find the steady state and make linearization and characteristic equation and use all these theorems that I give you to check the conditions for stability and instability of steady state. It's not difficult, but it's too much work. You have to, because, yes? Yes. Yes, exactly. Let me check here. It's more than that, because when you put let me check derivative x and derivative. No, here determinant will be 0. Yes, because they are separate. They are not in the same line. Yes, it will be also 0. And also here, I think most of system determinant of B is 0. Because when you make linearization, you calculate first in terms of the delay, you will have minus bx, okay? Then you will have only y in the first one. In the second one, you will have only xt minus r for the linear part. When you put the matrix, you have 0, 0, and no, because y is in the top, then you will have, yes, you will have 0, 0 in the top, and then the determinant is also 0 in this part, and also here in this model. I think we have something with the matrix. Not if you have something non-linear, it's like here xt minus tau and minus bt minus, and also here yt minus tau and xt minus tau. In that case, you can have complicated matrix. But in general, it's determinant of the matrix B is 0. Okay, now I will talk about another problem, is what we call monotone dynamical system. This theory exists for more complicated system like distributed delay, many delays, but I will concentrate only on one dimension and only discrete delay. We consider this delay differential equation with discrete delay, and we assume here that the first derivative of f in terms of x and in terms of y are continuous. It's only to have existence uniqueness of the solution, and we add this condition. This is very important condition for the derivative in terms of second component is positive. That means the function f is an increasing function in terms of the second, in terms of these conditions solve many things. So many times we don't need the characteristic equation to have stability of steady state, and in general global stability. Because consequence of this is we call semi-flow. It's monotone, but be careful. It's an increasing function, but this is strange because I have to. You can have you can have a function not necessarily monotone, but each if you take for each time t. No, this is very difficult to plot. It's like this part is monotone when it moves like I cannot put it, and this part also is monotone like time. It's monotone in terms of t, but it's for our system we will not use it. It's not important for. It's only if you want to do this big theory about monotone dynamical system. We have this theorem, and it's important if we take two solutions of our system, x and y, for two initial conditions, phi and psi, and if the solutions are defined on minus r sigma, and if this initial condition is less than this one, then we have this property. In terms of, remember that the initial condition is this one. Condition, I will put it other color, is this one. If you take this one bigger than this one for each, that means for each value, this one is bigger than this one. It can be like this. Then the solution here and the other solution here, if you take each piece of the solution between t minus r and t, this piece will be bigger than the other piece. This is what that means, this property. You translate this piece here and this, and you will have like this one bigger than this one. And if you increase time, always they will be like this. This can be not especially increasing, but red one in each piece has to be bigger than the other one. Okay, we can have like something like this. And the other one has to be also like this. Each piece on the interval of long equals to r, this red one has to be bigger than. This is what the theorem tells you. And the consequence of this is very big, because we will have many results as this one. As we have this monotony, we have this theorem. If there exists a constant x r such that if you put here x star and here constant x star, this is positive. X star, for example, can be steady state, but it's not necessary. It can be here equals to 0. Okay, and if you take any solution associated to an initial condition, and if you take y like a solution associated to this constant, if this is a steady state, that means y of t will be the same. In that case, you will have this. If you take initial condition bigger than this constant, then x of t will be bigger than the solution given by this constant, and in the same time, y of t will be bigger than this constant. This is a very interesting result because it's very quickly. Maybe I have to take a real example because if we take a constant here, x star, and you take initial constant bigger than this constant, and you take solution from this constant, if it's steady state, you will stay here. If not, it will be like this, and the other one is bigger. This is x, this is y, x star. Okay, the only condition is this, under this condition. Okay, now I can put many things, and you will see that why this result is very, very important. For example, I can put if I put like this, beta positive, all the equation of like this are solved by this problem, because the derivative in the second, here I will put maybe h to make a difference. You can take here as you like, no linear part. If this is linear here, the function f of x of t and x of t minus r is f of x y given by minus s of x plus beta y. You see it's linear in terms of, then the derivative of f in terms of y is beta, and it's always positive. Okay, if you put in on the delay something linear with a positive constant, this is satisfied. This property is satisfied all the time. And now, how to satisfy this? If I calculate f of x star, it's minus plus beta x star, because I put, and look, this function has to be positive or equals to 0. That means h of x star has to be up beta x. You can take this h nonlinear as you like. If this function is, for example, I take beta here. This is beta x star. If you take h of x star less than this one, okay, such that this is positive because beta x bigger than h, you will have this assumption. And this, for example, I put it for all x star. That means if the initial condition is bigger than any, if you have this condition, if the initial condition is bigger of any constants, then the solution will be also bigger than. This is a very, very good result, because this is the first thing that we check. If you have a delay differential equation, first degree, you check the delay. If it's monotone, it solves everything. You will see the result after. Here we cannot see, it's only, we have also the opposite. with the same condition, the same. If you have phi less than x star, you will have the inequality in the other part. This is the result what related to this assumption. We consider two real numbers, m and capital M, and here we take a steady state of this delay differential equation, such that this steady state is between small m and capital M. If we have this condition for all x interval except for the steady state, then if for any initial condition that is between this small m and big M, then we have the stability of this steady state. This, it looks like the same result as for ordinary differential system. If you take ordinary differential system with this condition, we have the same result. Because it's, let's take here x star equals to 0 to see this condition. It's like this. What that means, x f. What that means, this this condition. If we take 0 as a steady state, that means if x is positive, f of x is negative. Okay. Because f of 0 equals to 0, 0 is steady state. I suppose that x star equals to 0. And if x is negative, as this is negative, has to be positive. Okay, and this gives you stability of steady state for ordinary differential equation. This is a classical. And we have here the same for delay differential equation, taking the same function as ordinary differential equation. But the only condition we have to add is f is monotone in terms of the delay, and have the stability of the steady state. Okay, this is, I do it here for 0, but we can do it for any other steady state. Maybe to remember you, if I put this g of x and consider ordinary differential equation, x prime equals g of x, this means that x prime is negative. And 0 is the steady state. That means if this condition like that, if x is positive, the derivative is negative. If x is positive, the derivative is negative. And if x is negative, the derivative is positive. And you have the stability of 0 as steady state is attractive of the solution. We have, it's the same idea here. Let's try to have an example. This is interesting because it's global. That means it's not, you know exactly what is your set of initial condition that give you this attractivity. It's not like, because the local stability tell you there exists a neighborhood of around steady state. If you take initial condition on this set, you the solution will go to this steady state. Here, you know exactly what is your set of attractivity. You can if you know small m and capital M, you know where to put your initial condition to global state. Let's consider this example. I already talked about it. I think, okay, yes, x of t minus r. The nonlinear function here has this form. Is a hyperbolic tangent between -1 and 1 has this form. And the derivative, because the function is the tangent here, it's exactly k. Okay? And if we put, we look for a steady state before, because this system has this form, f of x t minus r. Okay? The steady state it's x star equals the intersection between this function and this one. This function is it depends on, we can have 1 or 3 steady state. If k is less than 1, I think we have only 0 as steady state. If k is bigger than 1, we have 3 steady states. Okay? 0 is always steady state. Let's start with 0 to do the same. First, you can see the function is monotone. Then the derivative of f in terms of y is positive. You can see here the hyperbolic tangent. Okay, let's check the stability of 0 as steady state. Let's use this this theorem. We put x, f of x. We have this condition. Then we can try to use it. We calculate this. It's minus x square plus x I will do it. Let's take x positive and x negative. Yes. Sorry? Yes, we can do it by here, because if k is less than 1, if k is less than 1, then this is negative. Yes, because this is bigger than, if k is less than 1 and x is positive, because we have to make the difference between, we have to take off 0, of course. Then we have to check x positive and x negative. If x is positive, then we have tangent is less than x, because k is less than 1. We can check for the derivative. Derivative is k, and derivative, this one is 1. Then if k is less than 1, this one, because here we can check only the derivative. Okay? That means x f is negative. Okay, now if x is negative, we have the same, because as we multiply by a negative term, the other one is positive in the other side, but we will still have x is negative. Okay, that means this property is satisfied. Which value of m, small m and big M, we have to take to have this property? Which value of m to have this? It's minus infinity and plus infinity, because it's always, if you go, this one will be bigger than this one forever, and this one will be bigger than this one forever. Then small m is minus infinity and big M is plus infinity. That means this property is satisfied for all x between minus infinity and plus infinity. At the end, 0 is globally attractive if k is less than 1. That means for this system, if you make simulations, it will go all the time to 0. You can take the initial condition as you like, as big you like, negative or positive. The system will go to 0 because satisfy this assumption. Okay, this is very strong result because it's more than local stability, or it's global stability, and it works for any initial condition you choose. As we have this assumption, 0 will be globally attractive, and it's not difficult to satisfy. Now, if k is bigger than 1, what will happen? If k is bigger than 1, that means we will have something like, because it's the derivative is k, that means we will have something like this. And the function x is in this part. That means here we will have three steady state. 0, 1 here, and 1 here. It depends on k. We will not solve it. I know that I will have something that I can call maybe u, and here minus u. They are symmetric. Okay? Let's check if we can, because the system is monotone. This is always satisfied. Let's check if we can find small m and big M to have this assumption. We will not do it because it's not necessary. We can see here the curve. Look, from 0, I think it's better to take small m equals to 0 first and to check here, because the steady state is around this. And you can see that this part is bigger than this part. Okay, that means this part is bigger than this part. That means it's positive, and you are in the positive part. Okay? No, let's check. This part is bigger than the. Why I? There is something. Sorry? Maybe I put something not. This, it's bigger than this. That means this is positive. Ah, yes, because I have x minus, this is negative, x minus, this is negative, it's not positive. I am in the x negative, but x is less than u. That means x minus u, which is the steady state, is negative. Okay? Yes, it's this satisfied. And if I am here, in the other part, this is negative, but it works also. Okay, that means this property is satisfied for small m equals to 0 and big M equals to plus infinity, because after that it will never change. I will have always this if x is bigger than the steady state. At the end, small m? No, it can be 0. There is no assumption. There is no thing. Okay. Yes, yes, that's right. Yes, you cannot be near 0, but never 0. Then the result is if the initial condition is bigger than 0, then small number 0, and it will be attracted by this steady state. And we have the same, we can do the opposite. If we are here, we will be attracted by this steady state. Then here we don't need characteristic equation or yes, in this case 0 is if k, because here k greater than 1 it's stable. If k bigger than 1, 0 becomes unstable, and the other one becomes stable and attractive. Yes, exactly. There is problem, but I will not talk. If you take initial condition positive and negative, a part is positive and part is negative, what will happen? Because here you take initial condition completely bigger than m to go to steady state u, and in the other part you take this minus infinity and this 0, and you will go to this steady state. But if you take initial condition between negative and positive in the same time, like what will happen? This is very difficult problem, and because 0 is unstable and you take something around 0, it looks like a part will go there and part, it will be oscillations. No one will attract it because you attract a part of the initial condition and minus u attract the other part. And this is, it depends on the initial condition how you take it. Sometimes it can go to one, sometimes can go to the other, sometimes can oscillate between positive and negative, between u and minus u. This is a problem doesn't solve by this or other. The problem here told you, if you are take initial condition completely positive, you will go to u. If you take it completely negative, you will go to minus u. If you take initial condition part positive and part negative, you cannot conclude using this result. Okay, this is another problem. Yes, for this kind of signal, it's exactly what happens, because this is used for the signal. Of course, we have also this property, but because if we have something different from this assumption, we have this result. If, for example, suppose that this is the opposite, what will happen? You will go far from the steady state. This is the only, it will be unstable, but more than that. If you take initial condition between m and steady state, the solution will be less than small m, and will be in the other set. This is what we can call instability, but very big, because you will be very far from the steady state. Each time you take m, the solution will be bigger than m. Of course, the condition is different from the other one, but also f is monotone. This is always it's the general condition. This is exactly the result that I did. And yes, and you have this. If the initial condition is bigger than 0, you will go to u, and if it is negative, you will go to minus u, and if k is less than 1, also equals to 1, then 0 will be the only equilibrium, and it will be globally attractive, attract all the initial condition. And if k is greater than 1, 0 is unstable, and we have two steady state. Each one is attractive. This result is more interesting than local asymptotic stability, because we know exactly the region of that attract the solution. It's not only to say that there is a neighborhood. We know exactly what is the region of that attract the solution. Oh, before talk about the Lyapunov function, because this the condition that condition is very strong. That means all the functions that we know, they are not satisfying this assumption and its problem. I will take example. If you take this famous one, I will make normalization and put, this is Nicholson blowfly equation. We don't have this assumption because the nonlinear part f of x and y is given by minus delta plus p y exponential. And the part that where there is delay has this form. It's not monotone. Okay, and this is problem, but the result of monotone dynamical system was generalized also to this kind of function by putting this. This is not monotone, but we know that it is monotone here, for example. It is increasing here. If this is the steady state is solution of this equation. That means it's a solution of delta equals to solution of this equation. That means the intersection between, there is 0, maybe I didn't put it correctly. It can be here if the result tell you if the steady state is in the part where the nonlinear function that contains the delay is increasing. If the steady state is this part but not this part, you can still use your result of monotone dynamical system to have a global stability of the steady state. Okay, how they do that? It's by comparison. They take this function and make it like monotone by putting this, adding this line. And this system, for example, if I put this new function, I will call it h bar of y. We can see that x prime is less than minus delta x of t plus h of xt minus r. And here we have we use a comparison result, comparison theorem that I already talked about. And we use this new function that is monotone to, as the steady state of this one is the same as the steady state of the other one, because he's in the part where the function are the same, we use this new function and comparison principle to have a global stability of this steady state. And this is works very well also. What we can say, every function that contains the delay, you can have a global stability in the part where the function is increasing. In general, when you move this, you have global stability. Let me show you general. This is the part that contains the delay. Okay? And this is the part that doesn't contain the delay. It can be nonlinear, it's not necessary. Something like this. For example, here there is only 0 as a steady state. As this part is increasing, 0 will be globally attractive, globally stable, because we can use here monotone dynamical system. The second part, if we are here, I will put like this. The part that contains the delay is still increasing. Here also we have a global stability of this steady state. And when you go until here, you lost global stability, you have only local asymptotic stability. And if you continue to move, you will arrive someplace when you will have Hopf bifurcation and oscillations around. If you continue, you will have Hopf bifurcation and oscillations. And this is depend all the time. This is one thing that the nonlinear part, the part that contains the delay, if it's decreasing, it creates oscillations. If it's increasing, it creates global stability of the steady state. All the time, and there is, because this result is very, very difficult. It's not, it was proved for many systems that you have global stability here until like a limit after the top. You have global stability. This is very hard to prove. And there is a threshold. After this threshold, you have local stability. And if you continue to decrease this function, you have appearance of oscillations and Hopf bifurcation and periodic solutions. And you can continue to decrease and you have more oscillations. This is really depend on if you are in the part that is with delay or without delay. What I can say to summarize this, all interesting system for delay differential equation has this form. This is the general. Plus, I will put here H plus G X T minus R. It has this form. And this is important to check this function G. This is all the time almost negative, and this is positive. And in general, if your function G is increasing, this is a good news, because you can use monotone dynamical system. If this part is decreasing, you will have Hopf bifurcation. And here you have to satisfy the monotone dynamical system. You will have attractivity, or you will go far from the steady state. But you will never have oscillations with the steady state around the region when the nonlinear part that contains delay is positive. If your function G has this form all the time, there is nothing to do, because if this is G and F is like this, you will have a global stability of this steady state all the time. Okay? There is two steady state. This one will be globally asymptotically stable. If you have something like this is G, and F like this, never cross again, this will be globally asymptotically stable. This is G and this is F. This is F. H, sorry. Stable, yes. Here, 0 is globally stable. Only 0. And they say there are two steady state, but this one is unstable and this one is stable, globally stable. Because it depends on the derivative here also, if it's bigger or not. Yeah, dynamical system give you this. Of course, this is the easy case when you have G monotone. The other case, you have to, G, for example, can has this form. Sometimes it can have like this. You have to select the part where it's increasing and the part where it's decreasing. The part where it's increasing, you have global stability, but doesn't mean that it works. It's very difficult to prove. But in general, we have this result because you put like, you make increasing function and principle to have a global stability of the steady state. In most of the problem, it's like that. Also for, yes, but of course, it's give you condition to have global stability. Mean you are you have the exact condition, necessary and sufficient condition. This is one problem that before that I put this. It's only, you see this Nicholson-Blowfly differential equation. I don't know if you can see. This is the history for global stability to prove. For example, in 1992, it was proved by Lyapunov function under this condition. This is exponential delta tau minus 1, p over delta minus 1 less than 1. And just after, in this year, with other people, they make like a small improvement to prove that, in fact, we have global stability even if it's equal to 1. And it was proved by hands, because this is the limit what we can do. And here it was proved also by the logarithm of p over delta less than 1 by these guys, by monotone dynamical system. And Hal Smith also, he make improvement to more. But until now, I think this is not the last year, because it was, I think, in 2015, we make like a small improvement, but it's not yet finished, because this is still open problem to have the exact condition of global stability. Each one had, because as the function is not monotone, and we don't know exactly what is the, because here I forgot to tell you, when you have this kind of function, you are sure to have a global stability here. There is no problem. But what we prove that the global stability go like little more, more when we are in this part. And this is the threshold to find, which each one add like a small. We know that there is like a limit, because after that it will be oscillations and Hopf bifurcation, but no one was able to find the exact limit. This is why there is competition each time to push this limit more and more. And until now, this for this simple Nicholson-Blowfly equation is still open to find the exact of global stability. This is because of no monotonity when we go in the other part. We don't know exactly. As I was talking about Lyapunov function, there is another way to prove global stability is using what we call Lyapunov function. And for delay differential equation, we have also, I will take my, it's more complicated, but we can construct Lyapunov function that it's the same idea as for ordinary differential equation. The only problem here, it's the Lyapunov function is functional. It's not, it acts on this function. But the idea is the same. If you are able to find like energy such that along the solution, the derivative of this is negative, you have a Lyapunov function. But it's not enough. You have to satisfy these conditions to have a global stability of steady state. That means your Lyapunov function has to be between two functions, u and v, this, and the derivative has to be less than another function w that is increasing and satisfy this. I will give you some examples. I think it's interesting to understand like that because it's if I take one, it's only two. The linear one. This is, I will put it. T minus r. And the Lyapunov function that we find is this one. You calculate the derivative and you put it on the solution, and mu is to find, and we find that mu has to be equal to b over 2. It's not difficult to, when you have this, you have to prove that the derivative of this function, if you put it on the solution, is negative. Okay, is less than, let's say, minus epsilon x of t, something like that, or square maybe, yes. W is, let's say, minus, W is epsilon, and we have to find epsilon. Okay, we always do like that. You calculate the derivative, and you put it in the solution. Here we will have xt prime xt, because you have square, plus mu. Here we make change of variable. You put t minus r t, and you put here s. Then it's x squared t minus s squared t minus r. Okay, you calculate, you put the derivative, then you have a x square plus b x xt minus r plus mu and minus mu. Yes, you put like this. It's not difficult to calculate, but the problem is to find the Lyapunov function, the form of the. After that, if you are lucky, it's okay. If not, it's difficult. And what we do here has the form A plus mu plus B you can see in our Lyapunov function, we have always to take off the delay. How to do it? It's like this has this form. I will put it like this, xy minus mu y square. And I want this to be less than minus epsilon x square. Then I put it here with this, and I calculate the discriminant and ask this discriminant to be independent on y. That means it's negative, and it has the sign of the big component. You know, it's like this is the easy part. It's not. I put both together. Then I have to solve the problem A plus mu plus epsilon x squared plus bx y minus mu. I want this to be negative all the time. To be negative all the time, I take like polynomial of x and calculate the discriminant, which is this one, minus 4 plus mu plus epsilon mu. And this is interesting because it's independent on y. You can see here, this is the idea. I want this to be negative. If this is negative, that means this is negative all the time. And this is negative. If I take this negative and this negative, it solves my problem. You know, because it's second degree. If this is negative, that means there is no roots, real roots. That means this has the same sign all the time, and it is the sign of this coefficient. If I choose this coefficient negative, then I will have this negative. Understand? This is, I will explain here, because I want this. This is a polynomial, okay? Polynomial. If I check that the discriminant is negative, that means I don't have a real solution. That means I am here or here. But if the coefficient here is negative, I am here. I cannot cross this. There is no real solution. Then it's negative. This is exactly what I want. Okay? Sorry? This? I don't know, because I don't know yet. Yeah, yes, of course. Epsilon positive, A, I don't know. I have to find condition on A and find mu and epsilon. If I am able to find any epsilon, any mu, it solves my problem. But until now, this is what I did. This is the condition that will give me stability. I take off y because it's square, the same. You see? I have this. Then I can take off and only the parameter. That means b square minus 4a plus mu plus epsilon. Mu has to be negative. And a plus mu plus epsilon has to be negative. Which condition give me this? I can choose mu and epsilon as I want. Positive. This is I can choose. If I can choose mu and epsilon positive to have this, it's finished. But remember, this is negative. Okay? This is negative because I have no choose. This is negative times this is positive, and this is positive. There is problem. No, there is a problem. What I did? This is negative. No, there is problem. Maybe I change how I did. This is has to be negative. No one say that I make mistake here. It's plus. Yes. Oof. No, now it's okay. Then can we choose epsilon and mu? And which condition? If A is positive, we cannot choose because this is negative. We have, that means A has to be negative. Because has to be negative. Yes, I can make more, like develop this and okay. I can give you one solution. Yes, I find it. We develop this mu square, make calculation, blah, blah, blah. And the solution that I find is mu and epsilon equal to this, has to be positive. And the condition is minus A minus B has to be positive. And this is exactly the condition of stability of 0 as a steady state that I already did. And here we prove that it's globally stable. It's more than local, because we find the same by, because yes, the condition here tell you that A has to be bigger than B and A has to be negative. Yes, yes, positive. Yes, mine's, sorry. And A is negative. This is how to compute Lyapunov function. I think most of them has the form that I give before. Huh? Do you have a question about this? For example, for our, I didn't talk about for the Lyapunov function that I wrote, it's automatically satisfied because you have, I don't remember exactly. I think it was 1/2. Yes, u of t, the function u, it's this one. And the function v of x, it's, I think, constant y, something like that, because we have to. And w is exactly epsilon square. We find this function because it's necessary to have to find the function that are increasing and satisfy all to have Lyapunov function. If you have questions or maybe I will stop here because yes, exactly. Yes, here we have interpretation. Yes, because the interpretation is is always in the same problem, because as for ordinary, when you check, if you take, I take this one, very easy. Lyapunov function for this is when you calculate the derivative for ordinary differential equation, you have x prime of t, and you calculate, and it's minus alpha x squared. Okay, it's exactly minus alpha 2 v of x. And this is, as this is positive, this is decreasing. This is decreasing, that means we will not cross 0, we will go to 0. For the Delay differential equation, you do the same, you have the same, but the problem you can cross. You can cross 0, because as I told you before, for the Delay differential equation, we can cross the steady state. And we cannot prove that we will go to 0, because you can go. And to do this, we make this, yes, we need this between the one and the other one, because here we are talking about 0 as a steady state. We always come back to 0. Not to cross 0, we make this limit. Yeah. Here, in general, for the Delay differential equation, you have two forms. Quadratic form, it's for the part without delay, and integral one for the part with delay. Yes, always, I can show you, I didn't write, but for example, this third function, you have quadratic one with 4, and integral with 6, because it's around it. No. Yes, also for discrete delay. Yes, because we make between t minus r to t. Then we can, by derivative, we can take off this. Because the idea, when you have delay, is to, when you calculate the derivative, it take off the delay. This is the idea. Because the problem told you here, at the end, you will have something without delay. This is what we put, phi of 0, without delay. This is all the time things that when we construct the Lyapunov function, we have to cancel all the terms with delay to find the Lyapunov function to cancel them. I will send you the PDF of the presentation. You can, yeah, but not put it in website, because as there are many figures coming from from books, or sometimes they don't like. Yes, but we can. Yeah, yes, of course. And if there is maybe many mistakes, because I do it very quickly, if there is something, you can send me a message to change. To have. Thank you.